The simplest cope rearrangement is the degenerate rearrangement of 1,5-hexatriene. As drawn in the given diagram, this 3,3 sigmatropic shift may take place by one of two transition states, a lower energy chair state or a higher energy both state. Because the product is identical with the reactant, isotopic labeling is needed to establish that change has occurred. The relatively high activation energy of this reaction requires a temperature near 300 degrees Celsius. If ring strain is relieved in this rearrangement, as in the case of cis-1,2 divinyl cyclopropane, the activation energy is substantially reduced so that conversion to 1,4-cycloheptadiene occurs below 20 degrees Celsius within 30 minutes. This rearrangement becomes degenerate for the compound bicyclo 5,10-octa-27-diene, and the activation energy is further reduced. In both cases, a boat transition state is forced by the structural constraints. If tricyclic analogues are formed by bridging the C1 and C8 carbons of bicyclo 5,10-octa-27-diene, similar degenerate rearrangements are observed. For three of these compounds, the activation energy is even lower due to a combination of increased ground state strain and transition state stabilization by interallylic bonding. The remarkable C10H10 hydrocarbon Bullvalene is exceptional in two respects. First, its ground state is stabilized relative to the dihydro analog by pi conjugation with a three-membered ring. Second, its threefold symmetry permits numerous self-replicating cope rearrangements leading to over 1,000,000 identical valence tautomers. All the carbons and hydrogens in Bullvalene appear to be equivalent on the NMR scale at 100 degrees Celsius and cannot be discriminated until cooled to -15 degrees Celsius. Molecules of this kind are termed fluxional. It is important to recognize that valence tautomerization of this kind is not resonance. That is, the relative positions of the atoms undergo small changes. Before studying the fluxional isomerism, let us first study about fluxional molecules and their properties. Fluxional molecules are molecules that undergo dynamics such that some or all of their atoms interchange between symmetry equivalent positions. Because virtually all molecules are fluxional in some respects, like bond rotations in most organic compounds, the term fluxional depends on the context and the method used to assess the dynamics. Often a molecule is considered fluxional if its spectroscopic signature exhibits line broadening, that is beyond the dictated by the Heisenberg uncertainty principle due to a chemical change. In some cases where the rates are slow, fluxionality is not detected spectroscopically but by isotopic labeling. Temperature dependent changes in the NMR spectra result from dynamics associated with the fluxional molecules when those dynamics proceed at rates comparable to the frequency differences observed by NMR. The experiment is called DNMR and typically involves recording spectra at various temperatures. In the ideal case, low temperature spectra can be assigned to the slow exchange limit, whereas spectra recorded at higher temperatures correspond to molecules at fast exchange limit. Typically, high temperature spectra are simpler than those recorded at low temperatures, since at high temperatures the equivalent sites are averaged out. Prior to the advent of DNMR, kinetics of reactions were measured on non-equilibrium mixtures, monitoring the approach to equilibrium. Many molecular processes exhibit fluxionality that can be probed on the NMR time scale. Other classic examples include the Cope rearrangement in Bullvalene and the chair inversion in cyclohexane. For processes that are too slow for traditional DNMR analysis, the technique spin saturation transfer, that is SST, is applicable. This magnetization transfer technique provides rate information provided that the rates exceed 1 by T1. So, after studying this module, you shall be able to 1. Know what are fluxional molecules, 2. Learn mechanism of fluxional tautomerism, 3. Identify examples of degenerate Cope rearrangements, 4. Evaluate fluxional tautomerism in Bullvalene, and 5. Analyze fluxional isomerism in organometallic compounds. By the introduction, Cope rearrangement, it is a pericyclic reaction involving 3,3 sigmatropic rearrangement of 1,5-dienes. These rearrangements can be performed thermally or photochemically. The Cope rearrangement of dienes has found utility in a number of regioselective and stereoselective synthesis of open ring systems. As you can see in the example, the sigmatropic rearrangements are an important class of pericyclic reactions which are classified based on an order which is expressed by a set of 2 digits in brackets I and J. These numbers are determined by counting the atoms over which each end of the sigma bond has moved. Each of the original termini is given the number 1. Thus, as can be seen, Cope rearrangement represents a 3,3 sigmatropic shift. Now let us talk about degenerate Cope rearrangements. According to IUPAC, the molecular rearrangement in which the main product is indistinguishable from the main reactant is called a degenerate rearrangement. The term is used for both intramolecular and intermolecular transfer of atoms or groups. The presence of degenerate rearrangements is most appropriately visible by isotopic labeling or dynamic NMR techniques. The degenerate rearrangement of 1,5-hexatriene is the easiest illustration of Cope rearrangement upon heating to 300 degrees Celsius. The Cope rearrangement may take place via one of the 2 transition states, either involving a lower energy chair form transition state or a higher energy boat form transition state. As the product is indistinguishable from the reactant, therefore, we use isotopic labeling to ensure that change has occurred. Unlike Claisen rearrangement, which also involves 3,3 sigmatropic shift with conversion of vinyl ethers into carbonyl double bonds, shifting the equilibrium completely to the product side, the Cope rearrangement is reversible. Thus, the position of equilibrium of Cope rearrangement is determined by other factors such as substitution patterns, conjugation, ring strain and other factors. Degenerate Cope rearrangements are a type of valence isomerization reactions. Valence isomerization are reversible in nature and generally rapid degenerate rearrangements that involve the formation and rupture of single and or double bonds without migration of atoms or groups takes place. Valence isomerization gives rise to fluxional molecules. An elegant example for multiple degenerate Cope rearrangements is shown by Bullvalene. Its chemical formula is C10H10. There is an unusual property associated with it, that is, the chemical bonds making up the molecule are continuously rearranging. In Bullvalene, the Cope rearrangement may change the position of the cyclopropane ring from 3, 4, 5 to 1 to 8 position. But the molecule could also have undergone rearrangements to put this ring at 1, 7, 8 or 4, 5, 10 positions. Any of these could then undergo several different Cope rearrangements and yet do not change the fundamental structure of Bullvalene. The mentioned reaction is known as infinitely degenerate Cope rearrangement, which shows the degenerate Cope rearrangements in Bullvalene. Molecules such as Bullvalene are called fluxional molecules. Fluxional molecules might undergo dynamics in such a way that some or all of their atoms interchange between symmetry equivalent positions. In fluxional tautomerism, compounds maintain the same number of component atoms like in the simple tautomerism. At equilibrium, these fluxional molecules exhibit several different isomers and fluctuate rapidly among them. Bullvalene molecule contains a threefold axis of symmetry and three symmetrical and equivalent Cope systems are thus available to it. Each of these 1,5-diene units can undergo a Cope rearrangement again, yielding Bullvalene. In all, there are more than 12 million tautomeric forms possible for Bullvalene. At 140 degrees Celsius, the reaction is so rapid that only one peak is being observed for all hydrogen atoms in the 1H NMR. With 3 double bonds in the Bullvalene system, it should exhibit chemically non-equivalent protons in the NMR spectra. However, due to its fluxional structure, it gives a sharp singlet in its proton NMR spectrum. This made it clear that in order for the 10 protons, each bonded to a carbon atom, to be chemically shift equivalent, all 10 carbon atoms must inevitably wander over the surface of a sphere in ever-changing relationship to each other. In general, fluxional molecules are a unique class of molecules with no permanent structure. Almost all molecules are fluxional in certain respects. For example, bond rotations in many of the organic compounds. A molecule is considered to be fluxional if it shows line broadening in spectroscopic signature due to chemical exchange, which is beyond Heisenberg's uncertainty principle. A few common features of fluxional molecules are: fluxional molecules behave differently at different temperatures. While interchanging between different conformations, many intermediates and metastable forms are reached. Fluxionality provides diversity in structure of a molecule. Several analogues of Bullvalene, such as semi-Bullvalene and barberylene, also exhibit the phenomena of fluxional isomerism, as can be seen in the structures. It was proposed that 3,4-homotropylidene exists as rapidly interconverting chair-like and boat-like conformational isomers, and the Cope rearrangement takes place by way of the higher energy boat-like isomer. Unlike other cases where Cope rearrangement is favored by a chair conformation, in the case of 3,4-homotropylidene, the rearrangements take place via a boat conformation, as shown in the above conformations drawn for 3,4-homotropylidene. The interactions between H1 and H5 promote the chair conformation, while positions of H2 and H3 are similar to Cope transition state in the boat form. You can see the boat-like structures and the chair-like structures. The chair to boat transition and Cope rearrangement of 3,4-homotropylidene. Overall, for the reaction, the activation energy for the Cope rearrangement includes the difference in energy between the two conformational isomers, as well as the free energy of activation of the Cope process. Another classic example of a fluxional molecule is dimethylformamide. The two methyl groups in dimethylformamide are indistinguishable at higher temperature. However, near room temperature, separate signals are seen for the non-equivalent methyl groups in high resolution NMR. The rate of exchange has also been calculated for this process at the temperature where the two signals are just merged. Let us now look at some reactions of molecules exhibiting fluxional isomerism. Optically active NN-dibenzylidene 1,2-diphenylene diamines rapidly racemize at low temperature and loses its optical activity due to fluxional isomerism in a Cope rearrangement via a 4-center chair transition state. Heating at 120 degrees Celsius in dimethyl sulfoxide gives a 1:1 mixture of DL and the mesoforms. Next, laderane are an interesting class of compounds containing 2 or more fused cyclobutane rings. The name arises from the resemblance of a series of fused cyclobutane rings to a ladder. A useful mechanism for synthesis of laderanes involves a 2+2 photocycloaddition, which is a useful reaction for creating the strained 4-membered rings. In a study, it was shown that shiftomer, structure number 2, is fluxional at room temperature and undergoes degenerate Cope rearrangement to give rise to 2' structure, which is equivalent to structure number 2. Continued indefinitely, the Cope rearrangement process leads to a pair of double bonds running down the polymer chain, running back and forth along the polycyclobutane network. Next, in another set of reactions, cyclooctatetrene, structure number 1, undergo dimerization to give structure number 2 as the major product. In a recent study, the fluxional nature of dimer of cyclooctatetraene 2 with unsaturated ketones in a Diels-Alder reaction was examined. The compound 2 can act as a reactive diene in Diels-Alder cycloadditions. It is also well known that structure 1 might as well undergo fast electrocyclic ring closure into its bicyclic valence tautomer number 3. But this electrocyclization is not thermodynamically favorable, and thus only a small amount of structure 3 is present at equilibrium. It was shown in the study that it takes a very small structural distortion at the dihydrobullvalene end of the molecule to dramatically change the NMR spectrum of this fluxional moiety, that is the dimer. Next, let us look at fluxional tautomerism in inorganic compounds. Many organometallic compounds also exhibit fluxional tautomerism. For example, the iron complex dicarbonyl eta 5 cyclopentadienyl cyclopenta 2,4-diene 1-yl iron, as shown, exhibits the phenomena of ring whizzing. In the molecule, there are 3 types of chemically non-equivalent protons. However, at 30 degrees Celsius, the 1H NMR spectrum shows only 2 peaks, one typical for the eta 5 C5H5 ring and the other assigned eta 1 C5H5. The singlet assigned to the eta 1 C5H5 ligand splits at low temperatures owing to the slow hopping of the ion center from carbon to carbon in the eta 1 C5 ligand. Simple molecules such as NH3 and pentacoordinate molecules of trigonal bipyramidal geometry also exhibit a particular kind of low energy fluxional behavior called Berry pseudo-rotation. Examples of such molecules are iron pentacarbonyl, that is FeCO5, and phosphorus pentafluoride, PF5. At higher temperatures, only one signal is observed for the ligands, example by 13 carbon or F19 NMR, whereas at low temperatures, two signals in a 2:3 ratio can be observed. It has been reported that the Berry pseudo-rotation mechanism is a type of vibration causing molecules of certain geometries to isomerize by exchanging the two axial ligands for two of the equatorial ones. Let us now summarize what we have so far studied. Cope rearrangement is a pericyclic sigmatropic 3-3 shift. Molecular rearrangement in which the principal product is indistinguishable from the principal reactant is called a degenerate rearrangement. Simple Cope rearrangements in 1,5-dienes are degenerate in nature. Bullvalene is a hydrocarbon with a chemical formula C10H10 with the unusual property that the chemical bonds making up the molecule are constantly rearranging. Bullvalene may undergo 1209600, that is more than a million Cope rearrangements, and still maintain the same structure due to its fluxional nature. Fluxional molecules might undergo dynamics in such a way that some or all of their atoms interchange between symmetry equivalent positions. Fluxional molecules behave differently at different temperatures. Cyclooctatetrene undergoes dimerization to give an adduct, which is a fluxional molecule. Laderanes are an interesting class of compounds containing two or more cyclobutane rings. They may exhibit phenomena of fluxional tautomerism. And lastly, many simple inorganic molecules such as PCl5 and FeCO5 also exhibit the phenomena of fluxional isomerism.